Today we're going to look at section 9.6, the counting principle. This section is really important if you're planning to go on to take statistics. A lot of the concepts that we're going to be learning in this lesson are concepts that you're going to have down pretty well as a base for your statistics. If you're not planning on taking statistics, even what you learned today is very practical for a lot of real world uses. So we'll get started. So the counting principle, specifically the multiplication principle. This is fairly intuitive, but if there are m ways of performing a task A and n ways of performing a different task B, then there are m times n ways of performing task A followed by task B. Note, this generalizes to the multiplication principle involving more than two tasks. So if there's more than two tasks, we just keep multiplying. So for example, a man has a choice of 8 shirts and 3 different pants. How many outfits can the man wear? Considering shirts as task 1 and pants as task 2, we have, well, simply 8 shirts times 3 pants equals 24 different possible outfits that the guy can wear. How many outcomes are possible for a game that consists of rolling a die followed by flipping a fair coin? Now there's 6 sides to a die, so there's 6 possibilities. And then for a coin, there's 2 sides, heads and tails, so there's 2 possibilities. So it's simply 6 times 2 gives us a total of 12 possible outcomes. All right, counting possibilities. An employee ID for a particular company consists of the employee's first initial, last initial, and the last 4 digits of his or her social security number. How many possible IDs are there? Well, if you think that each initial has 26 possibilities, and each digit has 10 possibilities from 0 to 9, well then, there's 26 possibilities for each letter times 10 possibilities for each number, each digit, gives us a total of over 6 million different possibilities. So that's one way of trying to assume that there's going to be uniqueness in the employee ID for that company, because there's assuming there's not that many employees. All right. Dinner at Angelo's. Diner at Angelo's Spaghetti Bar may select the entree from 6 varieties of pasta and 28 choices of sauce. How many such combinations are there that consist of just one variety of pasta and one kind of sauce? Well, we're going to multiply the number of pasta abilities times the number of sauce possibilities. So 6 times 28 gives us 168 different combinations that you can have of pasta and sauce. All right, possible answer patterns on a test. You have a math test that has 5 multiple choice questions with 4 options for each question. You must answer each question. How many different ways can you answer the test? So if you have no clue and you just want to guess on each answer, well, how many different possibilities are there? Well, there's 5 different questions, and there's 4 options for each question. So there's 4 possibilities for each answer. So it's simply going to be 4 to the 5th power, 4 times 4 times 4 times 4 times 4, or over 1,020 or over 1,000 possibilities. So your chances of getting all 5 questions right just by guessing are pretty small, because there's 1,000 different possibilities that it could be. All right, In the state of California, car license plates consist of a number followed by 3 letters and then 3 more numbers. How many possible cars could be licensed in California before they have to start repeating? Well, the first digit, there's 10 possibilities for the first digit. There's 26 possibilities for each letter. And then there's 10 possibilities for each of the last 3 digits. So you multiply that all together, and you're going to have 26 to the third, so 26 times 26 times 26 times 10 to the fourth, 10 times 10 times 10 times 10 gives us over 175 million different license plate possibilities in California. So it's going to be a while before they run out, but um, it will happen eventually, and then they'll have to come up with some different system or start back at zero. All right, let's switch over to the in-class practice. This won't take long. These are pretty simple. Let's go find them. All right. So a cafeteria offers a combo which consists of a sandwich and a drink. If there are 5 different sandwich and 4 different drink available, how many different combos are possible? Well, 5 times 4 is 20 combinations. So 5 different sandwiches, 4 different drinks. 5 times 4 is 20. Right. There are 12 daily flights from Chicago to Boston, and then 4 daily flights from Boston to Providence. How many different ways are there to fly from Chicago to Boston on the first day, and then from Boston to Providence the second day? Well, there's 12 ways to do it the first day, and then there's 4 different ways to do it the second day. So it's going to be simply 12 times 4, or there's 48 different flight combinations. All right. The Sweater Hut in the middle of the mall sells cardigans and crew neck sweaters. There are 10 sweater patterns, and each pattern comes in 3 sizes. In order to have a complete assortment for the hut, how many sweaters are required? Assuming you have just one of each, there's 2 different styles, there's 10 different patterns, and 3 different sizes. So 2 times 10 times 3 is equal to 60 sweaters. Not too hard. All right. Tossing a coin. A coin is tossed 3 times, and a sequence of heads and tails is recorded. Determine the number of possible outcomes. Well, if I'm going to toss a coin 3 times, there's 2 possibilities for first, 2 possibilities for the second, 2 possibilities for the third. So there's 8 different possibilities. But what are all those possibilities? Let's take a look. Well, the first coin could either be a heads or tails. The second coin after each of those could be a heads or a tails. And the third coin after each of those could be a heads or a tail. So here's your 8 possibilities. 1, 2, 3, 4, 5, 6, 7, 8. 8 possibilities. All right, a combination lock is unlocked by dialing a sequence of 3 numbers, first to the left, then to the right, and then to the left again. If there are 40 digits on the dial, determine the number of possible outcomes. Well, there's 40 ways to do the first number, there's 40 ways to do the second number, and there's 40 ways to do the third number. So that's simply 40 to the third power, which will be 64,000 different combinations for that lock. All right, this one's got a lot of words, but it really isn't that hard of a problem. But let's read through it. An investor has decided to purchase shares in the stock of 3 different companies. One is engaged in aerospace activities, one involved in energy development, and one involved in electronics. After some research, the account executive of a brokerage firm has recommended that the investor consider stock from 5 different aerospace companies. Okay, so he's going to pick one of the 5. 3 energy companies, so then he's going to pick one of the three, and 4 electronics companies, so he's going to pick one of those 4. In how many ways may the investor select a group of 3 companies from the executives list? So simply, there are 5 different aerospace companies that he can invest in, times 3 different energy companies, times 4 different electronics companies. So we're just going to multiply those together to get the different number of possibilities. So from those 12 companies, okay, there's 60 ways to pick one from each. All right, let's go back to the in-class practice here. Numbers 4 and 5. If 4 people enter a room with 9 chairs, in how many ways can they be seated? Okay, so this one isn't just 9 times 9 times 9 times 9 because we have to think about it. There's 9 ways for the first person entering the room to sit down, but the second person's not going to sit on his lap, so there's 8 different possibilities for the second person. Now 2 chairs are taken. That leaves 7 possibilities for the third person, and that leaves 6 possibilities for the last person. So now I can multiply those together, and I've got 3,024 seating arrangements. This is similar to the one we had before. There are 12 daily flights from New York to Toronto, 15 daily flights from Toronto to Montreal, and 8 daily flights from Montreal to New York. How many different ways are there to fly from New York to Toronto to Montreal and then back to New York on 3 consecutive days? So there's 12 ways to fly on the first day, there's 15 ways to fly on the second day, and there's 8 ways to fly on the third day. So we're simply going to multiply those together. 12 times 15 times 8 equals 1,440 different flight combinations. All right. All right. So I'm going to introduce a term here called permutations. Now, we use permutations when we are not using all of the available items and order matters. So if I'm looking at the number of ways people could come in first, second, third place in a race, well, that's certainly who comes first, who comes second, who comes third matters. Okay. If we're running a race and I want to align the participants, well, it makes a difference who's in lane 1, 2, 3, 4, 5, and 6. Okay. If I'm making a pattern on a bracelet and a pattern of beads, well, it certainly matters what order I put the beads in order to get the patterns that I want. So permutation is represented by this capital P. So it's NPR, which is represented as the number n factorial divided by n minus r factorial. Now, the good news is that that function is available on your calculator. It's under the math functions. If you go over to where it says prob for probability functions, so if you go to math, go over to prob, then you'll see that there is an NPR and there's also an NCR, and then there's also the factorial there. So n items take an R at a time. So we'll look at an example here. In a track meet, the 400-meter heats will be run in the morning, then the top 8 finishers will race the final in the afternoon. How many possible different lane assignments can occur for the 8 qualifying runners? Again, order matters, okay? Being in the first lane is different than being in the 8th lane. So this is going to be a permutation, NPR, and we can solve it this way. It's 8 and we're going to choose 8 different people from that 8. That turns out to be 40,320 different lane arrangements for these 8 runners. All right, combinations, when order doesn't matter. Okay, so we use combinations when we're not using all of the available items, and order does not matter. For instance, if I'm, ordering lunch at McDonald's, it doesn't matter if I order a Coke and then a hamburger, or a hamburger then a Coke. That's the same meal. That's different than a permutation. If I'm dealt cards in a hand, it doesn't matter which one I'm dealt first and which one I'm dealt last. Either way, it's the hand of cards that I have. Okay. If I'm looking at marbles, it doesn't matter if I have, a blue and a green or a green and a blue. That's the same thing, right? So the order doesn't matter. So we're going to use this notation. This should look very familiar because that's what we used last time. It's the exact same formula that we used in Pascal's triangle last class. So this is n items chosen r at a time, or n choose r. So let's take a look at an example here. How many different 12-person juries with 2 alternates can be chosen for a murder trial from the 50 selectees in a jury pool? I actually was on a jury panel once, and they kicked me off. They didn't like me, so I didn't get to be on the jury. But I found out later in the newspaper that the guy was actually found guilty of murder. So it would have been fun to be on the jury. But anyway, in this case, it doesn't matter where the people are sitting, right? They're still on the jury, so there's no difference in where you're sitting in the jury. You're on the jury, so that's in the case we're going to use a combination. So 50. I'm going to choose 14 because I got 12 jurors and two alternates, so 14 turns out to be over 937 billion different combinations of jurors. Quite a large number. So again, you can try plugging this number into your calculator under the math functions, math probability functions, and should come up with this. Or you can also use factorial and do it this way. Um, but try that on your calculator. Make sure that you can come up with that. All right, let's switch over to numbers 6 through 7. A robber has stolen a locked briefcase. The lock on the briefcase can be opened with a 3-digit code consisting of digits from 0 to 9. How many different codes are possible if the digits may be used more than once? So if it's a simple 3-digit number, well, it's just 10 times 10 times 10 equals 10 to the third, or 1,000 codes. So not too hard to break. How many codes are possible if digits are maybe used more than once? So here I've got 10. Maybe used only once. Sorry, I've got 10 possibilities for the first number, but since the one number has already been used, that means there's only 9 left for the next number. Now 2 have been used. That means there's only 8 that are left for the last possibility. So I could write that as 10 permutations of 3 objects are 720 codes. All right, let's take a look at number 7 here. Each employee at a large company is to be issued a computer ID code that consists of 3 letters followed by 2 digits. How many ID codes are possible if repetition is allowed? Well, that's 26 for the first digit, letter, 26 for the second letter, 26 for the third letter, times 10 possible for the first digit, times 10 possible for the second digit. So 26 cubed times 10 squared is equal to 1.757600 million codes. How many ID codes are possible if letters may not repeat, but the digits may repeat? Well, you've got 26 possibilities for the first letter. Now, one of the letters has already been used, so I only have 25 possibilities for the second. Now, two letters have been used, and there's only 24 possibilities for the third letter. Digits may repeat, so I can have 10 possibilities for the first digit, 10 possibilities for the second, multiply them together, and I come up with 1,560,000 codes. Now, how about if neither letters nor digits may repeat? So we got the 26, 25, 24 again, but now for the digits, I've got 10 possibilities for the first, but since one of the digits has been used, I can't repeat it, so there's only 9 possibilities for the last digit. And now I've got 26p3 times 10p2 is equal to 1,404,000 possible codes. So make sure you look at these examples, and I think it will really help you on the WebAssign. All right, so that's all we're going to do. So go ahead and take a look at 9.6. Again, look at some of the examples in the book. I think that will really help you if you weren't able to get full understanding on this lesson from the slides, but go ahead and take it. And no, we're not going to have a quiz or a test coming up. So we will do something coming up, and I'm not sure exactly what, but it will definitely will not be a test. So, all right. So that's all we're going to do for today.